All right, in this chapter, we're going to look at parametric equations and polar coordinates, different ways to express a curve in the plane, and we'll begin with parametric equations and doing some calculus with them. So, normally, or what we've been doing up until this point, for the most part, is we represent a curve in the plane using what we would call a rectangular equation, right? That's where we have, an equation with just x's and y's, right? So often it's in the form, y equals some function of x. And that can tell you, if we kind of think about an object moving along a path, that could tell you, where that object might be traveling on that path, but it doesn't really tell you when. Like, it doesn't tell you the direction of travel. It doesn't tell you where it starts and where it ends. Just sort of tells you, like, at the end, here's the locations where this object might have been. Now, back in Calculus for Engineering, if you took that here at Vermont Tech, you might recall that we introduced parametric equations to introduce time into the scenario, right? So rather than having a single equation with x's and y's that to represent a path, we have a pair of equations. We have one equation for x and one equation for y, and they tell us, this equation here, we express x as a function of t, and that'll tell us the x-coordinate over time, and this will tell us, y equals g of t. That'll tell us the y-coordinate as a function of time. So for a given value of t, we can just find the x-coordinate and the y-coordinate separately, and then we know where it was at each value of time. So we call t the parameter. This is a pair of parametric equations where t is the parameter, and t varies over some interval. And it will give us a plane curve. And the first thing we're going to do is look at how we find the slope of a tangent line when we have our equations in a parametric form. So, a pair of parametric equations still defines a curve in the plane. And a tangent slope should still mean the same thing. It should still be a dy dx, right? A change in y compared to a change in x. And the way that we could still compute that if we're starting with parametric equations is by using Theorem 33. Dy dx is equal to dy dt divided by dx dt, as long as dx dt is not 0. And so we just find each of the derivatives with respect to t and do some division. So here's an example to start us out. Whoops. So we have a pair of parametric equations. X is sine of t, y equals cosine t, and we're going to find dy dx. So dx dt is cosine t, y is cosine t, so dy dt is equal to negative sine t. So now using Theorem 33, dy dx, this is dy dt divided by dx dt. That gives us minus sine t over cosine t, or negative tangent of t. There's our dy dx. Notice that dy dx is a function of t, all right? Now, if we're starting with a pair of parametric equations, right, x is a function of t and y is a function of t, it'll always be the case that dy dx is still a function of t. And this actually affords us a way to find higher derivatives. So that's what Theorem 34 is all about. So if we understand that the second derivative of y with respect to x is the derivative with respect to x of the first derivative, right? It's the derivative of the first derivative, but with respect to x both times. Then, using Theorem 33, this tells us that we should find the derivative with respect to t of dy dx right, which we've just found and observed will be a function of t still, and then divided by dx dt. So we only find dx dt once, so that's always on the bottom. And then similarly, we could find the third derivative by taking the derivative with respect to x of the second derivative in that same way. So we differentiate with respect to t the second derivative with respect to x, and then again divide by dx dt. Let's do another example. Here we've got a curve given by a pair of parametric equations. And we want to find the slope and the concavity at the point 2, 3. So the slope, this is dy dx. So we want dy dx, and we want to evaluate it at the point 2, 3. And then the concavity as well. So that will be the second derivative. So let's begin, right? We've got our two functions. X is the square root of t. I'm going to go ahead and write that as t to the 1/2. dx dt is 1/2 t to the negative 1/2. Our y function is 1/4 times t squared minus 4, so dy dt is 1/4 times 2t, or 1/2 t. So now we can find dy dx. We can get the first derivative with respect to x. So this is dy dt over dx dt. That will be 1/2 t divided by 1/2 t to the negative 1/2. Doing a little algebra, rules of exponents and whatnot, we get t to the 3/2. All right. Now, to find the second derivative with respect to x, we're going to differentiate with respect to x. We're going to differentiate with respect to t, dy dx over dx dt. Right, so dy dx, that's this. So we're just going to differentiate that with respect to t. That gives us 3/2 t to the 1/2. And then again divide by dx dt, which we found over here on the left. That's 1/2 t to the negative 1/2. And simplifying this gives us 3t. So now we have both the first and second derivative of y with respect to x. So let's see what's going on at the point that we're interested in, at the point 2, 3. So let's see, they gave us the xy coordinates, 2, 3. We need to evaluate dy dx and the second derivative with respect to x. Those are both functions of t. So we need to find what is the value of t that we're going to plug in. So to do that, we'll just use one of these equations, right? So I'll use, say, the x equation. I know that x is 2. And that means that the square root of t is equal to 2, and if we square both sides, we get t equals 4. We could also use the y equation and get the same value of t. So let's find the slope. We really want dy dx at the value t equals 4. And so that is, dy dx is t to the 3/2. So that's 4 to the 3/2 power. That is the square root of 4 cubed. So 2 cubed is 8. So dy dx is equal to 8. There's our slope. we could describe it as certainly the function has to be increasing, the curve has to be increasing there. And now we'll find the concavity. So the second derivative was 3t. So that's 3 times 4, or 12. And we have a positive second derivative, which means it's concave up. So just our general observation now about the curve at the point 2, 3 is that the curve is increasing, concave up. So we've just made an observation, based on our calculations about what the graph of this curve will look like at the point 2, 3. So right now I'm just going to take a little bit of time and show you how our calculator can graph parametric equations. So when you hit the y equals button, I've got something in there already. All right, so when you hit the y equals button, here's what we're used to seeing, right? A different equation for each y, function. Y equals a function of x, type of function, rectangular equation I might want to plug in. What we need to be able to do is plug in a pair of parametric equations. And so our calculator can handle that. Just hit the mode button, and down here you'll see function is highlighted. I'm going to arrow over to hit select parametric. Depending on the model of your calculator, it might just say par, P-A-R. So you put it in parametric mode. Now hit your y equals button, and what we have is it looks different now, right? So let me clear these out. So now you can see for each color, right, for each color curve, there's a pair of equations, x1t, y1t, x2t, y2t. So we're going to plug in this pair of equations into the x1t and y1t. The x1t is the square root of t. Now when we do this, so we have second square root, and then I hit, my variable button, which is usually an x button, but now that it's in parametric mode, automatically changes that to a t. And let's see, y1 is 1/4 times t squared minus 4. Okay, now the next thing we want to do is set our window. And if you hit the window button, this will look, some of it will be familiar. Like we have the x-min and the x-max. Now, our point that we're interested in is the point 2, 3. So I don't need my window, my xy window, to be that huge. So I'm just going to say go from -2 to 5, say maybe on both axes. But we also need to set these t parameters. So when does t start? Now right in the problem it says t greater than or equal to 0. So I'm going to leave that at 0. And then how far up values of t? Now we could go as far up as we want. I'm going to just leave it at 10. Usually I'll stick to 10 and then see how the curve looks. If I've not included enough, like if I've not allowed t to get big enough, you'll see that because your curve will just stop. It'll kind of establish like it's drawing a curve, and then it just sort of stops, and there's nothing left. And a lot of the time that will be an indication that maybe we need to let our values of t get bigger. And then this last part is important. This is t-step. That's how often do we want it to stop and plot a point, right? Because what it's doing is it's stopping at a value t, finding x and y, plotting that point. And then stopping at another value t, finding x and y, and plotting that point. The smaller value for t-step, the more accurate and more like finely accurate your curve will be. If t-step is too large, it could look like just like a connect the dots thing. So I usually try to make my t-step pretty small. I'm going to stay at 0.01. It'll take longer to graph, but that's okay. It won't take terribly long. And now let's take a look at this graph. So there is the graph, the curve, And it keeps going, right? But this is the window that we're viewing it in because we want to see what's going on at our point. And if I hit the trace button, which is next to graph, it's gonna ask me to plug in a value, or it's here at t0, x is 0, and y is -1. I'm just gonna hit 4 because that was our value of t. And then you can see x is 2 and y is 3. There it is. Clearly it's increasing, definitely concave up. So that is in agreement with what we found in our calculations. All right, let's try another one. This graph here, they've given us a graph. This is a Prolate Cycloid, and it's given by these two equations. Here's our x equation, 2t minus pi sine of t, and y is 2 minus pi cosine t. In all of these, as usual, unless specified otherwise, our calculator should be in radian mode. And this curve, it says, crosses itself at the point 0, 2, so we could see that here. And you see they've included little arrows, right? So we could see that it kind of starts in this direction, goes, and then turns around, crosses itself, and heads out in that direction. So it crosses itself, and we want to find the equations of both of the tangent lines at that point. So we're interested in the point 0, 2. That's an xy coordinate. So first, maybe let's find the value of t at 0, 2. And we should find two values of t, right? If it crosses itself, that means that it has reached that point twice as as t progresses. So let's find t at the point 0, 2. And I think I'm going to use the y-coordinate this time. So y equals 2. That means that 2 minus pi cosine of t is equal to 2. And, the only way that happens is if pi cosine of t is 2, which means cosine of t, the only way that happens is if pi cosine of t is 0. And the only way that happens is if cosine of t is 0. And cosine of t is 0 at the top and the bottom of the circle. So that's at t equals positive pi over 2 and minus pi over 2. Okay. Now, and you can see that they've actually sort of, in fact, already given us those values, but we could find them on our own. Now you might be wondering, isn't cosine also 0 at 3 pi over 2 and at, 7 pi over 2? And that's true, but at those values, the value of, x will be different. So this is the one that makes, if you, at plus and minus pi over 2, this gives us x coordinates of 0. So we want the equations of the lines, which means we need the slope of the line. That's all we need. They gave us the point, so we just need the slope of the tangent line for each of these two values of t. So let's find dx dt and dy dt. Let's start with x. X is 2t minus pi sine of t. So dx dt is 2 minus pi cosine t. Our y function is 2 minus pi cosine t. And so dy dt is a positive pi sine t. That means now we can find dy dx, and that is dy dt over dx dt. So that is pi sine of t divided by 2 minus pi cosine t. All right, so we have the dy dx as a function of t. Now we're going to evaluate at pi over 2 and minus pi over 2 to find our slopes. So at minus pi over 2, dy dx is pi times sine of minus pi over 2 over 2 minus pi cosine minus pi over 2. Sine of minus pi over 2, that's the bottom of the circle, and so this is -1. Cosine at the bottom of the circle is 0. So up top I have a minus pi. On the bottom I have 2. So minus pi over 2 is that slope, and now at positive pi over 2, plugging pi over 2 into our dy dx expression. So that's the top of the circle. At the top of the circle, sine pi over 2, that's +1. At the top of the circle, cosine is 0, so we get a positive pi over 2. And now we're just about done. We can put our tangent lines together. We know that our point is 0, 2. So when t is negative pi over 2, we get y minus 2 is negative pi over 2 times x. And at t equals pi over 2, the line is y minus 2 equals positive pi over 2 times x. And that's what we're looking for. And here, I just used the form y minus y1 equals m times x minus x1 to get, to make those lines. But you could certainly choose y equals mx plus b if you prefer. Okay. So, let's move on. Let's see. Our next theorem is about finding arc length, or the arc of a curve, or sorry, the length of an arc traced out by a curve. We've already done some arc length back in chapter 3 of our notes, right, when we did a whole chapter on applications of integration. And there, if we had our curve was y equals f of x, right, a rectangular equation, then our arc length was, we integrated the function square root of 1 plus f prime squared with respect to x. And that was over the interval from a to b, and so those were our limits. This is similar. We are integrating with respect to t this time, but you can see that the formula, the integral formula looks pretty similar, but we're just going to take the sum of the squares of the two derivatives. So dx dt squared plus dy dt squared. Throw that under a square root. Integrate with respect to t over the interval from a to b. Now, this interval from a to b, that's a t interval, right? So the t interval, because we're integrating with respect to t. I've written the formula twice just based on whether you like the dx dt notation versus the prime notation. They mean the same thing. We're going to do an example. So imagine, we've got this circle of radius 1, and that's the little circle that we see right here, right? And so it starts on this end, and what we do is just roll it around this bigger circle, the circle of radius 4, right? That's the big circle, and we're just taking the little circle and rolling it around. Now, if you fix a point, say this point that starts right here, and then trace that point as it moves around, as the smaller circle rolls around the bigger one, it forms this curve that we see in black here. It's called an epicycloid, and we are going to find the length of this path as it starts and then returns to its starting point. Now, if we look up here at the theorem, the way that the theorem is stated, it says that we have a smooth curve given by these parametric equations, and that does not intersect with itself except possibly at the endpoints. Then that gives us this, the arc length is given by these integrals. Smooth curve means like smoothly differentiable. Like a smooth curve is what we see, say, like right here, right? That's a nice smooth curve. But what is not smooth is what happens at each of these points, right? There is no direct, if you think about drawing a tangent line at that point, there's like a million different tangent lines. It is not sort of continuously differentiable at that point. So we need to recognize that, and that's one reason why if we're doing an arc length, we always want to make sure we're looking at the curve, try to detect any of these problems. So what we're going to do is find the length of just one of these, and then we're going to use the symmetry of this. We'll multiply that length by 4. Now you can confirm this by throwing in these values, but at this point here, that's a value of t equals 0. That happens at t equals 0. And at this point here at the top, it hits that point when t is equal to pi over 2. So what we're going to do is integrate from 0 to pi over 2 and multiply that by 4. So this is going to take a little bit of space for sure, and what I'm going to do is sort of front load some of the work right up here to give us plenty of space down below. We know that we're going to need dx dt and dy dt, so I'm just going to find that and throw these up here. So dx dt. So here's our x function. Dx dt is a minus 5 sine t. Let's see, plus 5 sine t. Plus 5 sine 5t. And dy dt, that will be a 5 cosine t minus 5 cosine 5t. Now, I'm going to simplify these, or just sort of write them in what I think is a convenient way. I'm just going to factor out a 5 from each of these. So dx dt is 5 times, and I'm going to write this as a subtraction. So sine 5t minus sine t. And dy dt, going to factor out a 5, and that is cosine t minus cosine 5t. Okay, now notice what we need here. Just look at the formulas. We've got to square both of these, right? So we're going to have to do a bunch of algebra, and that's okay. I mean, really, it's just foiling this out. So I'm squaring a product, so I square the factor of 5, and that's 25. And now I'm just going to FOIL out sine 5t minus sine t. So that'll be a sine squared 5t minus 2 sine t sine 5t plus sine squared t. And dy dt squared, that's 25 times, and now I'm going to FOIL this out, so that's cosine squared t minus 2 cosine t cosine 5t plus cosine squared 5t. Okay, now we can set this up. So our arc length S is given by 4 times the integral from 0 to pi over 2 of the sum of the squares inside this radical. So we're going to have to do a bit of writing. Alright, so that looks nice and long, but we could do some simplifying here. In fact, we're going to find that a lot of stuff simplifies. We have a common factor, we have a common factor of 25 inside the square root. So I'm going to pull that out as a factor of 5 outside the radical, and of course I'm going to yank it right outside the integral itself. So 5 times 4 is 20. And now what we've got, is square root of, okay, so I've got sine squared 5t I'm going to rearrange these terms. Sine squared 5t plus cosine squared 5t plus, and as I do it, I'm just going to kind of strike through to make sure that I keep track of what I've already accounted for. Then next we have sine squared t plus cosine squared t. And now what's left is minus 2 sine t sine 5t minus 2 cosine t cosine 5t. That's all under a radical, which we're integrating with respect to t. By now you probably know one thing we're going to do to simplify. Right, so this sine squared plus cosine squared of 5t, that's 1. Sine squared t cosine squared t, that's 1. So that'll combine to give us 2, a term of 2 inside. And then there's one other thing we're going to do. I'm going to tell you what this ends up being after we apply an identity, and I'm going to supply the details of that calculation or that simplification in a separate document on Canvas. But this, using the product to sum formulas, this is a minus 2 cosine 4t. Oh, for some reason up here I wrote an integral from 0 to 2, that's pi over 2. So we're integrating from 0 to pi over 2. And I've got the 1 plus 1 is 2, minus 2 cosine 4t. Alright, now, so the next thing we're going to do is use another identity. You can use the double angle formula for cosine. And this becomes 4 sine squared of 2t. At this point, our path forward is clear, I think, right? We could take out, we have a factor of 4 inside the radical, so, and actually, what I think I'll do is simplify the radical itself, the whole thing. The square root of 4 sine squared is just 2 times sine. And we could take out this factor of 2. So now we have 40 times the integral from 0 to pi over 2 sine 2t. Now this isn't so bad. We know how to integrate sine. The integral of sine is negative cosine, but we do have to accommodate this factor of 2. We would need a factor of 2 here and then to divide by 2 outside. So we have 20 times, and once we integrate, we'll get minus cosine of 2t. This is from 0 to pi over 2. Let's see, at pi over 2, we end up with minus cosine of pi, which is minus a negative 1, which is 1, minus. At 0, we have minus cosine of 0, minus a negative cosine of 0, so minus a negative 1, and now that simplifies. 20 times 2 is 40. And there is our, there's our arc length. This is the whole arc length, right, because we already accounted for multiplying by 4 right at the get-go. Again, look for the details of using this product to sum formulas and the double angle cosine, right? These, this will be on a separate document posted. You'll see it's just using trig identities in a little algebra. All right, we did arc length, and so closely related to that, if we spend some time doing some arc length, is to do some surface area. Again, this is really similar. The integral formula is very similar to what we saw for finding a surface of revolution in Chapter 3. You'll notice that this additional factor of 2 pi in front, right, because we're revolving about an axis. And depending on the axis, so we're looking at revolving about the x-axis or revolving about the y-axis. And if we revolve about the x-axis, then the radius function will be the y-coordinate, which is why there's a g of t. And if we're revolving about the y-axis, then the radius will be the x-coordinate, and that's why we have this f of t. So both the g of t and the f of t here, that's basically like having an r of t, like a radius function, distance from the axis. So let's do an example. We're going to let C be the arc of the circle, x squared plus y squared equals 9. So there they've given us a rectangular equation, x squared plus y squared equals 9, from 3, 0 to 3 halves, 3 root 3 over 2. So this is the curve. We want to find the area of the surface formed by revolving this curve about the x-axis. All right, so first we need to represent this curve parametrically. So to represent this curve parametrically, the x-coordinate will be given by 3 times cosine of t. That figures out, right? First of all, this is a circle. The x-coordinate is given by cosine, but this is a circle with a radius 3. centered at the origin. So the x-coordinate will be 3 times cosine. The y-coordinate will be 3 times sine. And we're looking at this, if this curve, let's see, so starting at 0, and if we get to 3/2, that's 3 times 1/2, and cosine is equal to 1/2 at pi over 3. So now we have the parametric equations and the interval. So I think we're just about ready to go here. So we need our dx dt and dy dt so that we could set up our integral. So dx dt is minus 3 sine t. dy dt is 3 cosine t. Let's set up our integral. So we have 2 pi times the integral from 0 to pi over 3. Now we're revolving about the x-axis, and if we're revolving about the x-axis, it's the y function that is going to be our radius. So that's 3 sine t. So 3 sine t times the square root of the sum of the squares of the derivatives. So minus 3 sine t squared plus 3 cosine t squared. Gonna take out this factor of 3. So we got 6 pi times the integral from 0 to pi over 3. We've got a factor of sine t times the square root. Let's see, we get 9 sine squared plus 9 cosine squared. So I'm going to just take that out as a 9 sine squared plus cosine squared. Sine squared plus cosine squared, that's 1. And then we have the square root of 9, which will come out as a 3. So now we don't have a radical at all because that's just a constant. So we have 3, so that's 18 pi outside. Integrating from 0 to pi over 3, sine of t. Alright, I think we know where to go from here. The integral of sine is minus cosine. So we have a minus 18 pi times cosine t from 0 to pi over 3. Cosine of pi over 3 is a half. Cosine of 0 is 1. So negative 18 pi times a negative a half is a positive 9 pi.